This lecture we're going to kind of talk about MOS channel behavior, in particular kind of thinking about this from above and subthreshold regimes. Now you may have understood either the subthreshold or the above threshold regime at this point, but I want to talk about this as some of the unifying concepts. And from here you can kind of look in many different directions from here. One of the first things that you start to realize is that we're going to talk about the channel behavior in a MOSFET. We're going to start off, there is a subthreshold and above threshold region, and people will often ask, well, what is the break between the two? And when you think about it, that it really is one major thing. Sometimes you'll assume it's threshold voltage. And that's true only in particular kinds of experiments. Fundamentally, it turns out it has to do with the threshold current, particularly a saturated threshold current. What you're basically asking the question is, at what point do I have too much charge in the channel that's actually that basically requires me to, now deal with the charge in the channel and deal with those field lines as well as just the standard MOS capacitor that goes through the device. And we'll talk about a whole range of questions on looking at this. One of the things that becomes very important is that we do have a MOS capacitor right in this region here. That MOS capacitor we think about in one sense as two parallel capacitors, one of the oxide capacitance and one of the depletion capacitance. Very important pieces. Now, when I am looking at different regions, whether it be in depletion or inversion, I will have a different effect. Depletion looks like two parallel capacitors. Inversion looks like I'm adding additional charge at the surface. Because of the way the band structure is set up, it kind of forces that behavior. And in fact, if you think about it, we'll be able to ask the question in terms of what is the surface potential versus gate voltage, say, for a simple MOS capacitor. And it'll turn out that that potential will be something along the lines of a kappa VG in depletion, which is related to what we expect in subthreshold, and that would be that exact same kappa and same surface potential we might imagine in a very typical band picture. And it would be this surface potential that we would have, and we would notice it's flat in subthreshold. Why? Because we would expect that because the current is low enough, there is no change in the electrostatics all the way through. And therefore, when I look through my channel, I realize that this is really two 1D problems. I get in a separable sense. I have a MOS capacitor that is the same pretty much all the way throughout. And then I actually have the area along the channel, which looks like this very typical band picture. And all of this holds. Now, what happens is when I get above threshold, all of a sudden, now because of the way it behaves, the potential in the gate just can't move much further. And part of that's because I've reached sort of an inversion point where I can't get much further without the potential barrier actually getting near the conduction band or exceeding it. So that causes some major problems. So there has to be other ways to satisfy the constraints that I've got in the MOS capacitor. And it usually comes from bringing charge from somewhere to kind of help satisfy those constraints. So what will happen is the barrier won't change, but the charge will certainly increase. And what we find here is that the charge basically, the new addition of charge basically increases by the capacitance, by basically the voltage across the oxide capacitance itself. That makes subthreshold being very, very fundamental, almost a very pure sort of thing, and being just a very nice voltage control barrier, where this is controlled by the gate. These two potentials on the source and the drain are pretty much directly the exact potentials, because these are usually doped to be very highly doped. They're pretty much metallic, and so if I have a metal contact to it, I get a pretty good ohmic connection to it directly. And so I'm connecting pretty much Fermi level metal voltage right to the conduction band. Above threshold is going to be an interesting problem, because now this changes, because in above threshold what's going on in the channel is going to change with position. In fact, I would imagine the potential at this level will actually be lower than it will be here as I integrate over the additional charge that I'm bringing in. The other thing is that as I bring part of this channel in above threshold, I'm also going to run into this problem here, which is going to be that the potential is not going to move very much because I'm getting near the conduction band already, so I have to think about that. Okay, so what this tends to give you is interesting band pictures starting from, say, a nice subthreshold band I have up here. Imagine I have an experiment where I have the drain voltage high enough on an end FET so that I stay in saturation for a while. I am starting with a gate voltage that I'm going to sweep from a low potential to a high potential, source voltage at ground. Now look at the band pictures. Well, at a lower gate voltage, I'm going to expect to get a very nice subthreshold behavior. Surface potential here, source and drain where, potentials as expected. I'm going to keep the source and drain potentials the constant throughout the entire area. I'll have a noticeable source to channel potential and a source to drain potential on the side. Well, I'm going to increase the gate voltage. Initially, that would bring this potential down, and so I get exponentially more current. But at some point, it's going to reach a point where it stops, and I'm now going to start getting more current in this region. And as I do that, I'm going to get a decrease in the potential, approximated here to be roughly linear, which is not a bad guess, okay? It's a little off linear, but we'll kind of go with linear for this point. And I'm going to get some drop through there, and then I get to the end of the channel, and actually it turns out at that back end, this device becomes subthreshold in that part of the channel, in that part of the MOS capacitor. So I'm going to expect depletion in that device. And at that point, it pretty much just drops off, and so the electrons will just fall off the barrier just the same way they would have at above threshold or a subthreshold. The issue here is I've just lost a certain amount of potential. The amount of potential I have, it turns out, is related to the overdrive. So I lose that much voltage, and then the rest looks like a typical subthreshold device. I can continue decreasing this till this potential gets almost down to the drain side, pretty much right to the edge of it. And then at that stage, it's not going to move any further, and at that region, I'm usually in the area where we talk about a linear or ohmic regime, where I pretty much now have the barrier kind of stretches roughly linearly between the two potentials. And so this gives you a very sort of pictorial way, particularly in the band diagram, of what's changing in these systems. And this is really important to get a really good picture across both subthreshold and above threshold, and it also gets rid of a lot of fallacies. Fallacies like, for example, that the channel just disappears somehow in above threshold, which is, there's a tiny nugget of truth to that if you think that we all of a sudden became subthreshold. But for the most part, it leads things in the wrong direction in terms of really conceptually understanding what MOSFETs are doing. So hopefully this gives a good perspective over the overall concept of MOSFETs, and there's a whole lot more one could dig into any of these discussions from here.